thing. Oh, except for, what's that?
Is it 90 or?
That's an 88. Let's see here. I think everybody who's here has got their test. Let me begin with a word of prayer. So we're all here. Heavenly Father, we thank you for this day again. I thank you for this class, and just ask that you help us use the time wisely, just to review for the final, and just to draw the thoughts together for this class. In your name I pray, Lord Jesus. Amen. So let's see here if I can find my solution for test 4. We'll look at that. So at some point, like I'll just, my list of grievances. Like number one, someone asked me in here, would this be on test? And I said, in no uncertain terms, I said, well, yes, that would be on a test. I put that on many a test. And I think you guys thought I was joking, because I put it on the test and like, you guys were not ready for it, the sphere problem. So I don't think you're quite done studying basically for that one. And then the other thing is, like, just generically speaking, I was kind of surprised the general level of integration in here, because I felt like you guys did like way better on the quiz, but it occurred to me an obvious thing. The quiz was open notes. See? So what that means to me is a significant number of you need to set aside some time to just stop and memorize the basic things, right? Because you don't know them, you're looking them up every time you do them, and as such, you paid a price for that. The other problem is algebra, and I don't know how to fix that. Like, a lot of you guys are still getting a lot of stuff wrong because you're still making like incorrect algebra steps. And I can't fix that, you know? I'm not sure what to do about that. I mean, I hope it doesn't, you know, kill your grade in this class, but I really can't, I can't be like, have a way of passing people in calculus who can't do like the basic algebra stuff like that. That will stop you here, unfortunately. It's not like my mission or anything. It just happens. Like, I ask an algebra question and you guys are not able to do the algebra. So I'm talking about like simple things like multiplying x times x squared plus square root of x and like doing that, you know. Not that one so much, not that one really. More, I think the cube root of 27 problem got some people. Some of you remembered inverse cosine for that, which is interesting. I mean, you're not wrong, but you need a minus. Inverse cosine's got like a, because it's decreasing. So the derivative of inverse cosine is like minus 1 over 1 minus square root of minus x squared. There's that. Problem 2 is one of these even odd property problems. Problem 3, I don't think you guys are quite, you're not settled on like, okay, I have velocity, how do I find acceleration, how do I find a position? Not all of you, many of you did get the acceleration right here, which is good, but the position there was, well, anyway, some things happened. But I think half the class got this, maybe. Yeah. Okay, so anyway, if you guys have questions about anything, just jump in, all right? Yeah? I think a fair number of you got this problem, so that was good. Some of you missed the 11. Like, one person had like a 1/6 times that, which is, I don't know, things happen on the test, but it should have been 1/66, because when we take the antiderivative of u to the 10th, we get a division by 11. This one here, e to the u. So some of you are being very, what's the word? I guess careless with your notation, like you're not writing dx, you're not writing du where you should. This will get you into trouble. I do take points off for that. You really need to write something pretty similar to what I write, right? And I did say to show your, at the start of this problem, I say show work where necessary, indicate all U substitutions either implicitly or explicitly. That's why if you write the answer down for like the tangent problem, I'm glad you know it, but that's not a full solution, right? So that's why you lost points there. We're getting ahead of the story a bit here. Really only talking to one person. One person had the integral tangent memorized, which is a good thing. Good thing, you just haven't followed the instructions here. Okay, so this one here, this is more the one I'm talking about, the algebra. Like a lot of you, some of you, I should say, did things basically that amount to square root of a plus b being square root of a plus square root of b. Like square root, oh man, square root does not work like this. The reciprocal does not work like this. Like 1 over a plus b is not 1 over a plus 1 over b. Some of you are still, when you integrate quotients, you're writing like the integral of the top divided by the integral of the bottom. There is no such rule. All right? So that's not really worth much to me when you do that. In fact, I really shouldn't pass people who have that kind of calculational approach in here. Because if I let you through to Calculus 2, it's going to be a cycle of death and destruction. But anyway, because Calculus 2 is harder than this course. All right. Let's see here. This one's a lot like one of the problems we had on the, what was it, quiz or math battle? I can't remember. Math battle, yeah. So the difference was I threw a square in there. That changes it a bit because the integral of 1 over w squared is minus 1 over w, but the minus and minus cancels, you get 1 over w. And so we have that. Now some of you didn't put absolute values here. You really do need absolute value there. So watch out for that. Some of you have lost points by not adding a constant. This is easy to fix, right? Problems I can fix before the final easily. Remember to add a constant. We good? Okay. Cosine cubed, right? It's a standard problem here. We split off the square and then make a u equals sine substitution. This is how it goes. And I do think some of you got, everybody got one of these problems pretty much. These ones are fine. There's some problem later in the test that nobody quite got, but. So here we have, I fixed the double dx problem with my whiteout. Sorry. But anyway, if I make a u equals cosh substitution here, I've got d over 1 plus u squared, which integrates the inverse tangent. So I inverse tangent cosh. Quite a few of you got this problem right. Yay. I was happy about that. So part of the reason I'm emphasizing u substitution so much on this test is it is the skill that you really must have down pat to be successful in the first part of Calculus 2. When we start doing further integration techniques, at the base of all those is u substitution. So if you don't have your u substitution down really well, you'll be in a lot of trouble there. This one here, again, sine over cosine. So we make a u equals cosine, and we get minus the natural log of the absolute value of cosine x plus a constant, which of course you can rewrite as 1 over cosine, which is secant, if you like. Either one of those are fine answers. I think a lot of you got that, which is good. That was an example we did in class, right? Problem 5 is FTC3. Many of you still have not understood FTC3. I'm sorry about that. But it is what it is. So all you do is you take the integrand, right? And you plug in the upper bound. So I put e to the x here. I put e to the x cubed there. Then I multiply by the derivative of the upper bound, which the derivative of e to the x is e to the x. Then I take the integrand, which is cosh, and I evaluate at the lower bound, t plus t cubed, but t equal tangent, this and that. Multiply by the derivative of the lower bound, which is tangent, which is secant squared, and that is it. I see a lot of you guys like differentiating the cosh or doing various other things, but like it is just this. FTC3 is not more complicated than that. It's just that. So. many people got this problem wrong. All right, like problem 5, you got that wrong. Look around. Those are your brothers. So, I mean, you have lots of company. So, yeah. Now here, I was happy. I think a lot of you, a good number of you, at least had a reasonable graph, maybe better than mine. As you can see, mine is a little wiggly. And oh man, I was going to erase that. So I used horizontal strips, and I use since it's even, I just doubled the integral from from 0 to 2. 0 to 2 to get the integral from -2 to 2. There's a 2 that I could factor out of this as well, so I did that. I get me a 4. I try to factor numbers out as much as I can before the integral just to simplify the arithmetic. And it works out to 64/3, which I think about half of you got that. Something like that. A lot of you were kind of in the hunt, but you made an arithmetic mistake or something. A few of you had just completely wrong graphs. Just a couple of you like that. Anyway, so there's that problem. Let's go on here. So I thought more of you were going to get this because you guys did really well on the quiz problem that was like this, but maybe I'm just an idiot. Maybe I had a problem on the board which was like really, really similar to the quiz problem, so you guys just kind of like just twisted it or something. Was that it? Was that what happened? Could be. I don't know. I don't know, but it's 3/2. Now, there are other ways to do it. Like one of you had integral of x from, I think, 1 to 2. This could also be integral of x from 1 to 2. That would be a fine way to do it. There's infinitely many different ways to do it if you want to get weird. But anyway, there's this problem. So like, in terms of importance, understanding this problem is like here. Understanding U substitution is like up here, all right? U substitution, getting U substitution and the basic antiderivatives down pat is like way more important than problem 7.
There are going to be a lot of U substitution on the final.
Yes. Yeah, I mean, there can't be a lot, but there will be U substitution. There can't be a lot of anything on the final because the final has to cover everything. This one here, I told you guys during the test something magical happened, and I don't think it happened for any of you, unfortunately, and that's too bad, because I'd hoped that I'd assigned enough homework on the shells that you guys had learned it, and I don't quite think it happened for most of you, and that's unfortunate. But so here, if I think about the method of cylindrical shells, rotating around the x-axis, which means that my radius, y-axis rather, which means my radius here geometrically is r, which is r is equal to x, right? And so 2 pi x times the height, but the height is just 1 over x. So the x's, they be canceling, and you just get 2 pi dx. I was like, what? Cool. So yeah, just that. What's so weird is like, you know, if instead of being, it doesn't really matter that it's 1 to 2. Like you could make it go from like A to B, and the answer would just be like, you know, 2 pi B minus A. That would be the volume, you know. Like I don't know. I don't know how I hadn't run into this example before. It's really cool. Anyway. So, yeah, I'm sorry that didn't go better. Yes, as I said, dude. So like this problem has convinced me that you're not quite done studying for this test, right? I know it's the end of the semester. This course is very lengthy. There is much to do. You have other courses, you know, blah, 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 blah. But you should be able to do these derivations, like if they come back on the final, right? Yeah. Oh, by the way, I think I made the cone more complicated in class. Because what did I do in class? What's the difference between what I did here and what I did in class? It's a seemingly minor thing. But if you take the cone and you turn it upside down and put the base and make it the point side stick up, the formula for the characteristic size of the disk, it's much uglier. It's that like minus r over h times z minus h. My formula is just r over h times z. That works. See, s of 0 is 0, s of h is r, which is what you want. Like the radius of the disk at the top is r, the radius of the disk at the origin, at the point of the cone is 0, you know? So just in retrospect, retroactive apology for you guys that I did the example in class in the stupid way. Like it would have been much cooler if I'd done the example in class like this. This is a better way to do that example. On the other hand, I have no regrets in some sense because that way my example lined up with my pyramid example. But now that I think about it, maybe we could take our pyramids and turn them upside down and it would be easier to set up the formulas because the formula for the side length of the pyramid would be like something more of the form like z times a constant. If the pyramid is starting at like the side length being 0 at the point, if we calculate the volume from the point to the base, it might make the calculation easier actually. Just a thought. And the sphere is what it is. I'm glad that some of you know the formulas for the volume of a cone and volume of a sphere. That is good. That is healthy. However, as I said, via calculus for credit. So, sorry. This one here is a hard problem. That's why I put it last. But I have done this problem in class like about 3 times this semester. Yeah. And I think I have spent, I don't know, an hour and a half of class time talking about the techniques that are required for doing this problem, right? In terms of like completing the square, trying to, do the long division beforehand to get a proper rational function, looking for an arctangent piece and a log piece. And some of you have gotten elements of this. I don't think anybody got the whole thing. So, but this is pretty much like the hardest integration type problem I cover this semester, right? So if you can figure this out, then that's good. If you can't, well, it's not great, but I don't know how far you are from understanding this, is all I'm trying to say. It is important that you understand earlier things in the course more than this. I'll just say that. But I don't want to tell you to give up on this problem, but some of you are quite a ways from understanding it. All right, so that's that. Let's see here. So let's go back. Actually, you know what? Let me see if I can't find my final from like 2013. How about that? Let's look at my final. It's like idea. Here's the final I gave in spring of 2012. Problem 1, a bunch of limits. Minus infinity, 0, pi over 2, infinity. I don't know, I'd have to work out the algebra. 1. I know all of these from like the graphs of the function and or just thinking about how the formula behaves, right? So now, if I had a question like this and you don't remember the graph, what simple thing can you do to figure these questions out? You've got a calculator, right? All you got to do is take your calculator and try putting, 100 into inverse tangent, see what happens. Put 1,000 into inverse tangent, see what happens. Make sure you're in radian mode, right? Because we do radians for the calculus for the trigonometric functions in here. You should probably be able to see that it's going to like 1.57 blah, blah, blah. And maybe now that I've told you this, that's pi over 2, you'll remember it. But anyway, so, and like similar comments apply to all of these, is you could try plugging in numbers really close to the limit point to see what it goes to. Now, it's a question of time. That takes time though, right? So do you have time to do that? I don't know. It's better if you just know the answers, but all right. So next up, a warning. It's just a perennial problem in Calculus 1 is we hit anti-differentiation at the end of the semester, and then you guys start forgetting differentiation sometimes. So you'll start integrating where you should be differentiating. So check yourself on that, right? At the end of the test, once you've done everything else, go back, go through each of your calculations, and ask yourself the simple question: did I differentiate? Where should I differentiate? Have I accidentally integrated where where I should be differentiating? Right? Watch out for this. Yep. Mm-hmm. Sure. Yeah, I can post this. Let's see here. These, so, 1 over 2x, nx to the n minus 1, secant tangent, minus cosecant squared, 1 over x, minus 1 over x squared, minus sine x, sinh x, e to the x, natural log of 10 times 10 to the x. You should be able to do that problem in like a minute, right? You really should. This one here, integral of dx is x, integral of cos is sinh. I'd have to think about that one for a second. Inverse sine, that's a third minus a half minus a sixth minus cosine, 1 over log 3, 3 to the x. I'd have to think about it. Tangent, natural log of 1 minus natural log of 3, right? Oh, this final will be horrible to grade. Oh my goodness, this page would take me forever to grade. Why did I do this? I tell you why I did it, is that page is kind of a check, I can tell a lot about where the student is in this course on how they do on that page. That page shouldn't be a troublesome one, And then here, let's see, we're differentiating. So this one you got to do what? It's like a product rule and then a chain rule. This is, chain rule followed by product rule. Let's do that one. Let's work that one out. All right, let's see here. So we got, where was I? d dx of the sine of the square root of x times 2 to the x. So chain rule says that that's cosine of the square root of x times 2 to the x times the derivative with respect to x of the square root of x times 2 to the x. That's the chain rule, right? Then what happens?
You put the whole thing to the 1/2 and then use a
Put the whole thing to the 1/2 and make a u substitution. Kind of, sort of. I like what you're saying. Think of this inside as u, and so this is really u to the 1/2. That's the pattern. That's the right way to think of it. Absolutely. And so we've got cosine of, well, if I'm going to use that notation, this is the square root of u, and then 1 over 2 square root of u times du dx, right? So I've got cosine of the square root of u divided by 2 square root of u, and then I'm doing d dx of what? X times 2 to the x, right? But that is a product, so I must do the product rule. And so what I have at the end of all this is cosine of the square root of x times 2 to the x divided by 2 times the square root of x times 2 to the x, parentheses, 2 to the x plus x times the natural log of 2 times 2 to the x. And that's the derivative here. Oof. How about the next one? The next one down there. How on earth would you even do x squared plus x times x to the sine x power. And I won't do all these because you guys need to practice, right? Right?
So we do that last one, or we just saying it?
Yeah, I mean, I'm just saying I'm not going to do them all. All right, so you guys tell me how to do the next one, though. What technique do I need to use? I can't just differentiate this thing, right? Like, how do you differentiate stuff to the sine x power? There's no rule for that, all right? What you're looking at is a mixture of a power function and an exponential function. You have variability in both the base and the exponent. If you have variability both in the base and the exponent, you must use like the implicit differentiation technique. Like write y equals to this and basically do logarithmic differentiation to work this out. Excuse me. Find the equation to the tangent line. So what do we do there? We differentiate implicitly, calculate dy dx, and then plug in the point, right? Show the derivative of inverse tangents that. Okay, so let me just go really quick through this, the rest. Integration, u substitution, another u substitution. Oh. Oof. That one. It's a bit nasty. So that one, you're going to want to look at like making a u equals x squared substitution. And once you, it's not that bad. If you make a u equals x squared substitution, I think it then, I'm an idiot. This is not bad. I'm stupid. This is not bad at all. What is that? Oh, come on, good grief. You guys tell me how to do that one. There we go. It's just, and then the derivative du is 4x to the third dx, right? So that's literally du over u. So the answer is natural log of the denominator, absolute value, you know. That one's not bad. I was thinking it was worse. Anyway, well, that's interesting. How do you do that? Whoa, interesting. I'm not sure how to do that offhand, but I'm sure it reflects the homework that was given this semester. Can you state the main formulas for FTC1 and FTC2? What are they? I mean, these were like the big events of the course, towards the end at least. FTC1, the main formula for FTC1 is simply this: d dx of the integral from a to x of f of t dt is equal to f of x. That's it. That's all I'm looking for there as an answer. FTC2 is simply this: integral from a to b of f of x dx is equal to f of b minus big F of a, where f prime of x is equal to little f of x. Like that, there you go. This is FTC2, and this is the fundamental theorem of calculus part 1. We proved FTC1 implies FTC2 this semester. All right. I would not make you prove that on the final. All right. Don't worry about that. Oh, look. So, yeah. So how would you do this? What's problem 9? I'm differentiating an integral with variable bounds. How do you do that? It is the dreaded FTC3, right? So the answer would be, well, I'm not going to tell you the answer. You guys got to think about it. But the answer should involve h and g, and also derivatives of h and g. But it's, you know, again, FTC3 there. Now it's been a minute since we did this, but remember, back at the start of the course, we had a definition for the derivative. What was our definition for the derivative? You guys remember? there were two choices, right? We could do f prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. We could do like that. We could also do like f prime of a is the limit as x goes to a of f of x minus f of a over x minus a. But if I ask you guys to calculate the derivative from the definition involving a difference quotient, I am telling you what that means is you must give an argument that is using the limit definition of the derivative. So you have to work out the derivative using like limit laws. For instance, a typical question might be to, show the derivative of sine is cosine. From the limit definition, we work that out. That one's kind of a pain, but there are easier things like show the derivative of 1 over x is minus 1 over x squared, for instance. I'll get out the solution to our test 1 in a minute. We'll look at some of these if I have time. Hopefully we will. Linearization, approximation based on linearization, equation of the tangent line. How are tangent line and linearization related? Simply this. The tangent line is the graph of the linearization. Essentially, they're the same thing. The formula for the tangent line is y equals f of a plus f prime of a times x minus a. That's a line which goes through a comma f of a and has slope f prime of a. That's the tangent line. You should know that. You should be able to apply it. What's the tool to solve problem 12 here? Find the absolute extrema, or extrema if you like. Find the min-max for this function on the closed set 1 to 3. We use the what? Use the closed set test, right? Or if you like, the extreme value theorem. So what you have to do is find any critical numbers, set f prime of x equal to 0, find out what those are, and then you calculate f at any critical numbers, you calculate f of 1, you calculate f of 3, and you simply pick winners and losers. This is the closed set test. So how about the next problem? How would you guys solve that? What's this problem? What's the tool there? That limit is what? Infinity times 0. So we cannot use L'Hopital's rule yet, but what do? Rewrite it as x squared over e to the x. Then you've got type infinity over infinity. You can apply L'Hopital's rule. L'Hopital that thing 2 times, and you'll find out that the limit works out to 0. That's a L'Hopital problem. Whoa. What the? Whoa. Well, that's different. Well, okay. What? That's right. Okay. We talked about calculus and graphing, right? Find where a function's increasing, where it's decreasing. The intervals of concavity, up and down, inflection points, mins, max, local maxes, vertical tangents, horizontal tangents, all that jazz. Put all that stuff together to make a picture of graph. This is probably the more, I guess it's more than likely, arguably it's probably the most nuanced thing we've done this semester because there's just so many moving pieces. But I do typically ask at least one of those. I don't ask a bunch of them because they take a lot of time. And but anyway. Oh look, there's this problem again. And volume of a solid, set up but do not calculate. A herd of cows drink water from a triangular trough which is 10 feet long, whose cross-section forms an equilateral, blah, blah, blah. This is a related rates problem. But I wouldn't, you guys can skip this problem. This is not a problem we've done this semester, and don't worry about this one. I wouldn't ask this one because it wasn't in your homework. And nothing like it was in your homework. So this is not a reasonable question for you guys this semester. It was a reasonable question for them because they had problems like this. Yeah, I do customize the final to the semester, So don't read too much into this final either, But there are some commonalities. I always test on all the rules of differentiation. I always test on most of the integration techniques that we go over. I almost always test on, major statements of theorems like FTC1, FTC2. What's another theorem you should be able to state for the final? I mean, it's not exactly a theorem, but you need to know the definition of derivative, right? It would be good for you to know the definition of the integral, or in terms of Riemann sum, like we did, right? The other theorems that come to mind that I sometimes ask students to repeat are the mean value theorem and the intermediate value theorem, Rolle's theorem sometimes, the Fermat's theorem. I think that's all we've done. Extreme value, the closed set test, like the extreme value theorem, I don't oftentimes ask you to state it, but I almost always ask it a question which requires you to apply it. So in this class, I don't think we've had more than 10 theorems. That's not too much to remember, I think. I also want you to know that velocity is the derivative of position and that acceleration is the derivative of velocity. All right. Now this right here is not really calculus. This is a pre-calculus question right here. Show that inverse hyperbolic cosine is the natural log of x plus the square root of x squared minus 1. That was in your homework early on. So every once in a while I'll do something like that. I'll cycle back to an early homework and see if you guys have actually figured out how to do that thing. But as you can see, this is towards the very end of the test. So I forget, there were particular reasons this semester that I asked this question. Maybe I'd actually worked it out in class or something. So I wanted to see if they'd actually pay attention to like what I'd done in class. It could be something like that. That could be the history of this problem. The solution to it, the way you solve this problem is you write y equals inverse hyperbolic cosine of x. That gives you x is equal to cosh of y, but cosh of y equal to x gives you that x is equal to 1/2 e to the y plus e to the minus y, which then you multiply by e to the y. It gives you a quadratic in e to the y, which you then can solve. And then you take the natural log of that, and out pops this formula. So it's like, there's no calculus in there at all. It's just it's a standard pre-calculus calculation that you may or may not have seen. So this is a conceptual question about like inverse. In this particular semester, I spent a lot of time talking about the problem of injectivity and what's a local inverse for the function. That didn't happen for you guys, so I wouldn't foresee this question in this form for you guys. Problem 22, I think I more or less asked as a bonus question on like test 2 or 1, didn't I? Like p of x times e to the cx, where c is a constant, how many horizontal tangents are possible? I've asked a question like this in something I gave you guys, right? The thing is, if you differentiate a polynomial times an exponential, you still get a polynomial of the same degree times the exponential. So if p of x is order n, f prime of x could have as many as n zeros. There could be as many as n horizontal tangents. And I believe the same is true for like inflection points, for instance. How would you guys attack problem 23 here? Is x squared continuous? I think it is. Is x plus 3 over x squared minus 9 continuous? Not everywhere. It's got vertical asymptotes, right? So I mean, it's got some points of discontinuity at like, well, outside its domain, I suppose. Oh, but there's an x plus 3, so that could be a hole in the graph. I think this thing actually has a hole in the graph at minus 3. Oh, minus 3 is exactly the interesting point, right? So the question is whether or not the limit from the left and the limit from the right of this function agree at the gluing point at minus 3, right? So to answer this question, you must take the limit as f of x as x approaches 3 from the left, and calculate the limit as f of x as x approaches 3 from the right. If those limits disagree, the function's not continuous, right? We had problems early in the course where we had like a variable, and we could choose a value for the variable which would make the function continuous, right? Remember that? Oh, look at that. Volume of a square pyramid, height h, which has sides of length a. So, that is very much a possible question for your final. I would say it's more likely I ask about the sphere or the cone, given what just happened on test 4. So the history of this course would make that more likely. Looks like it. I mean, we're to question 25. That much I can say.
I think this one has like 250. Our final is like 200.
Oh, well, I just make your problems worth less. It's not like it's not written in stone, you know. Although I'm tired, so maybe I'll give you a shorter final. Let's see here. So prove by epsilon delta definition of the limit that that's true. It's been a minute since we did those, but that is part of the course. Let's see here. Ooh, look at that. I put these at the bitter end because these are nasty. You know, well, that one's not nasty. That's just a U substitution. That's easy. But when they're different, you need to know that trigonometric identity we worked out, right? So if you don't know that, it's hard to do that one. This derivative requires, I would say one defect of this final is I haven't explicitly forced the issue of logarithmic differentiation. I typically do that on a final. Like this is a little bit unusual in that regard. Although something or else has to give. All right, let me look in here for a second. We're almost done. Well, I guess that's it. So anyway, I would encourage you guys, like I said, look back over your tests, look back over the quizzes, and then look back over the homework in kind of that order. I should be in my office or in the math department during class time next week, but we won't have class, all right? So I'll see you guys at the final.